Okay, here we're going to talk about what the principle of superposition is. When two or more waves are simultaneously present at a single point in space, the displacement of the medium at that point is the sum of the displacements due to each individual wave. So over the right-hand side here, we see actually some constructive interference or destructive interference happening here. We have a wave coming in and a wave here, and then when they superimpose on top of each other down here, they cancel each other out, and there's destructive interference. So superposition means that two waves overlap. We need to understand what constructive and destructive interference is. In this case here, we have two waves coming in towards each other, and they both are up on the top part of the wave, and when they interfere, they make a bigger amplitude. When they superimpose on top of each other, they're a bigger amplitude. They do pass through each other and remain unchanged after they pass through each other. Down below here, we have destructive interference, and if you look at it, we can see that destructive interference occurs. On the left-hand side, we have a wave going to the right, and then we have another wave coming over here from the left, and then when they superimpose, they're flat, they destroy each other, and that's destructive interference, and then the wave continues on unchanged. Sometimes destructive interference does not make a flat line. If one of the amplitudes is larger and one of the amplitudes is smaller, when they superimpose on top of each other, you still have a smaller amplitude, though. That's still called destructive interference. Now we're going to look at what a standing wave is. And it's when individual points on the string oscillate up and down, but the wave itself does not seem to travel. So what we have here is three different types of standing waves. This wave here is called the first harmonic. It's m equals 1. It's the first harmonic. This is the second harmonic, m equals 2. And this is the third harmonic, m equals 3. And so each of these is a standing wave, and you'll notice that there's destructive and constructive interference occurring. There's destructive interference right here where a node occurs, and then there's constructive interference right here in these sections, and then that's destructive here and destructive here where the other node is. And the question is, what are nodes and antinodes? So the nodes are where destructive interference occurs. This is a node, 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 and node. Those are in red. So I have nodes in red. And then constructive interference occurs where the antinodes are. So constructive interference occurs right here and here, and that's where the antinodes are. We don't call it crests and troughs because at this point here, it's a crest, and down here is a trough. It just the wave, the part of the wave, the medium, moves back and forth from crest to trough. So we have to remind ourselves, how does a wave reflect from a more rigid medium? We can see here that the wave beforehand, before it hits the boundary, the more rigid medium, it comes in as a crest, and then you'll see it inverts and comes out as a trough. So for a more rigid medium, it inverts. For a less rigid medium, it stays upright. It'll come back on the same side. So what would happen is, if it was a less rigid medium, the wave would look just like above. It would come in upright, and then it would bounce back, but on the same side. It would come back out on the same side if this was a less rigid medium right here. So how a standing wave is created is, here's an example. What happens, we wiggle the string in the middle, and we send two waves out, one wave to the left and one wave to the right. They both reflect off the walls, come back in, and these reflected waves will travel through each other, and it will create a standing wave at that point. What will happen is there'll be points of constructive interference and destructive interference forming nodes and antinodes. So what happens is, in order for a standing wave to be created, you have to have these reflected waves superimposed on top of each other, have constructive and destructive interference, and then the standing wave will occur. Off to the right, we see the three harmonics, the first, second, third harmonic of standing waves. But we want to know what the equations for a string fixed at both ends and what that equation is when it's experiencing a standing wave. So what is the frequency? Well, let's go ahead and take a look. Here we have velocity equals frequency times wavelength. And so we can solve for frequency. Frequency is the velocity all over the wavelength. And this should work for any of the, the equation we're going to come up with should work for any of the harmonics. So we'll do our F sub m. We'll have wavelength sub m. Now the velocity, I don't do sub m because the velocity should be the same along no matter what harmonic you have. The velocity will be exactly the same. If it's a low frequency or a high frequency, the velocity will be exactly the same. So that's part of our equation, but let's plug into that equation something that'll help us out with converting this to a different equation. We're going to plug in for wavelength. And if we look over here, this length here is L. So for the first harmonic, our wavelength equals 2L. For this harmonic, our wavelength equals L. And then for the third harmonic, our wavelength equals 2/3 of L. So our wavelength is from here to here. Now there's a pattern here that we can use to help us to then plug in for wavelength in our other equation. So our pattern, our equation, if we look at this, is wavelength equals 2L over m. And that's because if you think about it here, you have 2L over here, m is 1. Here you have 2L over 2, m is 2. And so those cancel, so you get wavelength of L. And over here, its wavelength equals 2L over the third harmonic, 3. So it's 2/3 L. So it works in all situations. So we're going to go ahead and plug that in. And so we get our frequency equals V all over 2L all over M. And if we rearrange this, what we end up with is M being the harmonic times V all over 2L. So that's our equation for calculating the frequency of a wave on a string. M is the harmonic. L is the length of string. V is the speed of the wave on the string. And F is the frequency. I would like you to write down these different harmonics. So if you could pause the video and write down the first three harmonics. The first harmonic is also called the fundamental frequency. The fundamental frequency is also sometimes called the first harmonic. So I would like you to draw pictures of the first three harmonics just for practice. So pause the video, do that now, and I'll write them down now as well. So your three harmonics should look like this.